main topic is, does space end? Have you ever stood outside on a clear night, looked up at the stars, and felt that strange pull in your chest? That mixture of wonder and vertigo that comes from trying to grasp something impossibly vast? Tonight, I want to take you on a journey to answer a question that has haunted humanity since we first gazed upward. Does space actually end somewhere? Is there a cosmic wall, a final frontier, or does it just keep going? What I'm about to share with you might completely change how you think about the universe, because the answer isn't what you'd expect. In fact, it's far stranger, more beautiful, and more mysterious than any science fiction writer could have imagined. And by the time we're done, you'll understand why some of the brightest minds in physics lose sleep over this very question, while paradoxically, this exploration might help you drift off into the most peaceful sleep you've had in weeks. Before we embark on this cosmic voyage together, let me ask you something that might seem simple but holds profound implications. Where are you right now? Not just your city or country, but where in the universe? Are you tucked into bed in Tokyo at midnight? Sprawled on a couch in Cairo at sunset? Walking through Central Park with earbuds in? Drop a comment and let me know. There's something magical about realizing our little community is scattered across this spinning ball of rock, all of us connected by our curiosity about what lies beyond. And here's what's beautiful about this moment. You don't need to take notes. You don't need to memorize anything. Just let these ideas wash over you like starlight, ancient, gentle, and surprisingly comforting. Because sometimes the biggest questions in the universe have the most soothing answers. Though I should mention, this journey is purely for wonder and relaxation. It's not medical advice or professional treatment of any kind. So, settle in. Get comfortable. Let's begin with something that might surprise you. Space isn't nothing. That might sound obvious, but think about it. For centuries, even brilliant scientists believed space was just emptiness, a void, the absence of stuff. Like a giant cosmic warehouse with planets and stars scattered around like forgotten furniture. But here's where things get deliciously weird. Space is actually one of the most active, mysterious substances in the universe. It bends, it stretches, it hums with energy even in the darkest, emptiest corners where no star has ever shone. To understand what I mean, let's travel back to a time when everyone thought space was simple. Picture Isaac Newton, probably the smartest person of his era, imagining the universe as a vast theater stage. Space was the wooden floor, solid, unchanging, reliable. Planets and stars were merely actors moving across this eternal platform. Time ticked the same for everyone, everywhere. It was comfortable, predictable, almost boring in its simplicity. Then along came a patent clerk with wild hair, an even wilder imagination. Albert Einstein didn't just update Newton's picture, he shattered it completely. According to Einstein, space isn't a passive stage at all. It's more like a living, breathing fabric that responds to everything that happens within it. Mass and energy don't just exist in space. They shape it, bend it, twist it into curves and valleys. Here's a way to picture it that might blow your mind. Imagine a trampoline. Place a bowling ball in the center, and the fabric dips down. Now roll a marble nearby. Instead of traveling in a straight line, the marble curves around the dip, spiraling inward. That marble isn't being pulled by some invisible string. It's following the curve of the fabric itself. That's exactly how gravity works in our universe. We're not being pulled toward Earth. We're sliding down a curve that Earth creates in the fabric of space and time. But wait, it gets even stranger. Even in the vast emptiness between galaxies, in regions so dark and cold that no atom has visited for billions of years, space is still buzzing with activity. This isn't poetry, it's quantum mechanics. At the tiniest scales imaginable, scales so small that atoms look like solar systems, space is frothing with what physicists call quantum fields. These fields aren't things floating in space. They are space. Every particle that exists, every electron in your body, every photon of light from your screen, every quark in every atom, is just a tiny vibration in these quantum fields. And here's the kicker. Even when no particles are present, these fields never stop jittering. They're constantly producing pairs of particles that pop into existence and annihilate each other faster than thought. It's like the universe is constantly clearing its throat, maintaining a background hum that never quite goes silent. Scientists call this vacuum energy, and it's not just theoretical. We can measure its effects. It influences how electrons orbit atoms. It might even be responsible for the mysterious dark energy that's pushing our universe apart faster and faster. So next time someone tells you space is empty, you can smile knowingly. Space is many things: vast, dark, cold in places, but empty? Never. And perhaps that's the most comforting thought of all. Even in the loneliest corners of the cosmos, there's still something happening. A gentle vibration, a quantum whisper, a reminder that the universe is never truly still. It's like discovering that silence itself has a sound, soft, subtle, but undeniably present. This revelation changes everything about how we approach our big question. Because if space isn't nothing, if it's a thing with properties and behaviors and quirks, then asking where it ends becomes far more interesting. Can a fabric have an edge? Can a quantum field just stop? These aren't just philosophical musings anymore. They're scientific questions. You know, the world continues beyond that misty veil, but you can't see it. Not yet. This is exactly our situation with the universe, except our mist is made of time and light, and our hilltop is a tiny planet orbiting an ordinary star. You might think quite reasonably that if the universe is 13.8 billion years old, then we should be able to see 13.8 billion light years in every direction. After all, light travels at, well, the speed of light. But the universe has been playing a cosmic prank on us. Because space itself has been stretching this entire time, the farthest objects we can see are actually about 46.5 billion light-years away. Our observable universe, everything we could possibly detect, spans about 93 billion light-years across. Let me explain this mind-bending fact with something mundane. Imagine you're texting a friend who's on a train pulling away from the station. You send a message when they're 100 meters away. But by the time your message arrives, the train has moved, and they're now 150 meters away. The message traveled 100 meters, but your friend is 150 meters distant. That's exactly what's happening with light from distant galaxies, except the train is space itself, and it's been accelerating for billions of years. This creates what we call the cosmic horizon, not a physical barrier, but a limit to information. Beyond this horizon, there are almost certainly more galaxies, more stars, maybe even other civilizations wondering about the edge of their observable universe. But their light hasn't had time to reach us. It's still on its way, struggling across the expanding gulf of space like a swimmer against an ever-strengthening current. Here's something that might keep you up at night, or perhaps help you sleep, depending on your perspective. Some galaxies we can see right now are already beyond our reach forever. The light we're seeing left them billions of years ago when they were closer. But now, they're receding faster than light itself. Not because they're breaking physics, nothing can move through space faster than light, but because space between us is expanding so rapidly that even light can't keep up. It's like watching the taillights of a car disappearing around a corner. You can still see the red glow, but the car itself is already gone, heading down a road you'll never travel. Every night, more galaxies cross this threshold, slipping beyond the cosmic event horizon into a realm we'll never explore, never see, never know. And yet, and here's where it gets beautifully strange, everyone in the universe has their own observable universe. If you were standing on a planet in the Andromeda Galaxy, your cosmic horizon would overlap with ours, but also include regions we'll never see. Every conscious being in the cosmos is at the center of their own bubble of observability, each one unique, each one limited, each one a personal window into the infinite. This isn't a flaw in the universe's design. It's a feature. It means that no single observer can ever see everything. The universe keeps some secrets from everyone, ensuring that mystery and wonder can never be exhausted. There will always be something beyond the horizon, always another question to ask, always a reason to keep looking up. When you look at stars, you're not seeing them as they are, you're seeing them as they were. That bright star you're looking at, its light might have left when your grandparents were children. That faint galaxy barely visible through a telescope, its photons began their journey before Earth had oceans. You're not just stargazing, you're time-traveling, collecting ancient light like messages in bottles that have been drifting across an ocean of space for eons. This temporal displacement isn't a quirk or a glitch, it's the fundamental nature of our universe. Light, the fastest thing that exists, still takes time to travel. And given the mind-boggling scale of space, even light speed feels sluggish. The sunlight warming your face? It's 8 minutes old. The light from Neptune? 4 hours. The nearest star beyond our sun? Over 4 years. We live in a universe where now is always local, always personal, never universal. Scientists call this phenomenon look-back time, and it transforms every telescope into a time machine. When the Hubble Space Telescope captures an image of a galaxy 10 billion light-years away, it's showing us that galaxy as it was 10 billion years ago, when the universe was young, wild, and still figuring out how to make stars efficiently. We're seeing cosmic baby photos, preserved in light itself. But here's where it gets even more interesting. As light travels through expanding space, it stretches. Just like the sound of an ambulance siren drops in pitch as it moves away, light from receding galaxies shifts toward the red end of the spectrum. This redshift isn't just a curious effect, it's a cosmic timestamp, telling us how long that light has been traveling and how fast that galaxy is moving away from us. The farther we look, the more extreme this redshift becomes. The most distant galaxies we've detected are so redshifted that what started as visible light has stretched into infrared. We need special telescopes just to see them. It's as if the universe is speaking to us in an ever-deepening voice, its words stretching out into longer and longer wavelengths as they cross the expanding void. This creates a strange kind of archaeology. When astronomers study the early universe, they're not digging into the ground, they're peering into the distance. The farther out they look, the farther back they see. Every observation is a core sample of cosmic history, preserved in flight. And perhaps most remarkably, we can see back almost to the beginning itself. Not quite to the Big Bang, the universe was opaque for its first 380,000 years, but just after, when the cosmic fog cleared and the first light broke free. This ancient light, the cosmic microwave background, still fills the universe today. It's everywhere, passing through your room right now, carrying information about what the universe was like when it was less than 0.003 of its current age. Think about that for a moment. Light from the universe's infancy is hitting your skin right now. You can't see it, it's been stretched into microwave wavelengths, but it's there. You're being gently bathed in the afterglow of creation itself. Every square centimeter of your body is absorbing photons that have been traveling for 13.8 billion years, carrying messages from a time before stars, before galaxies, before the Earth, before the very atoms that make up your body. This ancient light has witnessed everything. It was there when the first stars ignited, turning on like streetlights in a dark universe. It watched as galaxies collided and merged, as black holes grew to monstrous sizes, as countless worlds formed and perhaps harbored life. And through it all, it kept traveling, spreading, cooling, carrying its encrypted history across the cosmos. The universe, in this sense, is like a vast library where all the books are flying toward you at the speed of light, but from different distances. The closest books arrive quickly, telling recent stories. The distant books take longer, carrying older tales. And the most ancient books, the origin stories of everything, are written in a language that's been stretched and shifted until we need special instruments just to read them. This cosmic library is never static. New books are constantly being written, even as old ones fade beyond our reach. Stars are being born right now whose light won't reach Earth for millions of years. Civilizations might be rising and falling in distant galaxies, their entire histories playing out while their light slowly crawls toward us across the expanding gulf. There's something deeply humbling about this. Every night, when you look up at the stars, you're seeing a patchwork of different times. That constellation you recognize. Each star's light left at a different moment. You're seeing them arranged not as they are, but as they were when their light began its journey. The night sky is a collage of history, a mosaic of moments that never actually existed together. Picture yourself back in that morning filled with a mist. But now imagine that the mist represents not just distance, but the limits of time and physics combined. These are the cosmic horizons, the boundaries of what we can know, not what exists. The particle horizon is our ultimate limit. It marks the farthest distance from which light could have reached us since the universe began. Currently, that's about 46.5 billion light-years in every direction. Everything beyond that horizon exists. We have no reason to doubt that, but it might as well be in another universe entirely. No signal, no information, no influence from those regions has had time to reach us. But there's another horizon, more subtle and in some ways more troubling, the event horizon of the universe. This isn't the dramatic kind that surrounds black holes. Instead, it's the boundary beyond which events can never affect us, no matter how long we wait. Galaxies beyond this horizon are receding so fast due to the universe's accelerating expansion that any light they emit now will never, ever reach us. Imagine throwing a message in a bottle into a river, but the current accelerates the farther downstream it goes. At some point, the river flows faster than your bottle can travel. Your message will never reach anyone downstream of that point. That's exactly what's happening in our universe, except the river is space itself, and it's speeding up. Right now, galaxies we can see clearly are crossing this event horizon. We can still see them because we're looking at old light emitted when they were closer. But their present selves, already lost to us forever. It's a cosmic farewell that happens in slow motion, played out over billions of years. These horizons aren't walls or barriers in any physical sense. You couldn't fly a spaceship to the edge and bump into anything. They're more like the horizon on Earth, always moving with you, always the same distance away, defined by your position and the geometry of space rather than any actual boundary. What's particularly fascinating is that these horizons mean the observable universe is actually getting both bigger and smaller at the same time. Bigger because light from more distant regions has time to reach us. Smaller because galaxies are falling beyond the event horizon, becoming causally disconnected from us forever. We're living in a unique epoch. Our ancestors saw a smaller observable universe. Fewer galaxies had revealed themselves. Our descendants will see a larger observable universe, but with fewer galaxies in it, as more and more slip beyond the event horizon. We exist in a sweet spot where the universe is old enough to be rich with visible galaxies, but young enough that they haven't all fled beyond our reach. There's a melancholy beauty to this. The universe is slowly drawing curtains across itself, hiding its distant reaches behind horizons we can never cross. Each passing moment sees a little more of the cosmos slip away, like sand through cosmic fingers. And yet, within our bubble of observability, there's still so much to see, so much to learn, so much to wonder about. In 1929, an astronomer named Edwin Hubble made an observation that changed everything. He noticed that galaxies weren't just sitting still in space like ornaments on a cosmic Christmas tree. They were moving away from us, and the farther away they were, the faster they seemed to be receding. It was as if the entire universe was swelling like a balloon. But here's the crucial point that even today makes people's heads spin. The galaxies aren't flying through space like rockets. Space itself is expanding, carrying galaxies along for the ride. It's not that things in space are moving apart, Space between things is literally growing. I know that sounds impossible. How can space itself grow? What's it growing into? These questions assume space is expanding into something else, like a balloon inflating inside a room. But that's not what's happening. Space isn't expanding into anything, it's just expanding. There's no outside, no container, no bigger box that holds our universe. The expansion is intrinsic to space itself. Here's my favorite way to think about it. Imagine you're a tiny two-dimensional being living on the surface of a balloon. As the balloon inflates, every point on the surface moves away from every other point. From your two-dimensional perspective, your universe is expanding, but you can't point to a center of expansion. Every point looks like the center from its own perspective. That's exactly what's happening in our three-dimensional universe, just harder to visualize. This expansion explains one of the most profound discoveries in cosmology. If everything is moving apart now, everything must have been closer together in the past. Wind the clock back far enough, and everything, all the matter, all the energy, all the space, must have been compressed into an incredibly hot, dense state. This is what we call the Big Bang, though that name is misleading. It wasn't an explosion in space. It was an explosion of space. The evidence for this expansion is overwhelming. We see it in the redshift of galaxies, in the cosmic microwave background, in the abundance of light elements. But perhaps the most shocking discovery came in 1998 when two independent teams of astronomers found that the expansion isn't just continuing, it's accelerating. Think about that. You'd expect gravity to slow the expansion down, like friction slowing a spinning top. Instead, something is pushing space apart faster and faster. We call this mysterious something dark energy, which is really just a fancy way of saying we have no idea what's going on, but we can measure its effects. Dark energy makes up about 68 of the universe's total energy budget. Let that sink in. More than two-thirds of everything is this mysterious force that's stretching space itself. It's like discovering that most of your house is made of rooms you've never seen, filled with furniture you can't identify, inhabited by something you can't describe. The acceleration has profound implications for the future. If it continues, and we have no reason to think it won't, then the universe will expand forever, growing colder, darker, and lonelier. Galaxies will drift apart until each one is isolated in its own observable universe. The night sky will gradually empty of distant lights until only our local group of galaxies remains visible. Eventually, even atoms might be torn apart by the relentless expansion. But that's trillions of years in the future. For now, we live in a universe that's expanding, but still dense enough with galaxies to be interesting, still warm enough to support life, still young enough to be full of activity and wonder. The expansion of space also resolves a paradox that might have occurred to you. If nothing can travel faster than light, how can galaxies be moving away from us faster than light? The answer is that they're not moving through space faster than light. Space between us is expanding, and there's no cosmic speed limit on how fast space itself can grow. This leads to one of the most mind-bending aspects of modern cosmology. There are galaxies right now that we can see. Their ancient light is just reaching us, but which are currently so far away due to expansion that we could never reach them, even if we traveled at the speed of light forever. They exist in our past, but not in our future. We can see where they were, but never visit where they are. It's a peculiar kind of cosmic isolation. We're not alone in the universe. We can see billions of galaxies, but most of them are already forever beyond our reach. It's like being at a party where you can see everyone, but can only talk to the people right next to you, and even they're slowly walking away. Yet there's something almost poetic about the expansion. The universe began in a state of incredible density and heat, a moment of ultimate togetherness. Since then, it's been spreading out, cooling down, creating space for complexity to emerge. Stars needed room to form. Galaxies needed space to spiral. Planets needed distance from their stars to develop stable orbits. Life needed the universe to expand and cool enough for chemistry to work its magic. In a sense, the expansion of space is what made everything possible. Without it, the universe would have remained a hot, dense soup forever. The very fact that we exist to wonder about the expansion is a consequence of the expansion itself. We are children of the growing cosmos, born from its tendency to spread and cool and create spaces where interesting things can happen. Here's a thought that might scramble your brain a bit. There are regions of space receding from us faster than the speed of light. Not because they're breaking Einstein's cosmic speed limit, but because space itself is stretching faster than light can travel through it. This isn't science fiction, it's happening right now, all around us at distances greater than about 14 billion light-years. Galaxies beyond that distance are being carried away by the expansion of space faster than 299,792,458 meters per second. Their light, despite traveling at the maximum possible speed, will never reach us. They're not violating relativity because they're not moving through space that fast. Space itself is doing the heavy lifting. To understand this, imagine you're on a treadmill trying to walk towards someone, but the treadmill keeps speeding up. Eventually, it's moving backward faster than you can walk forward. You're not walking any slower, you're still going your maximum speed, but you're losing ground because the surface beneath you is working against you. That's exactly what light experiences when trying to reach us from these ultra-distant galaxies. This creates a bizarre situation. We can see some of these galaxies right now. We're detecting light they emitted billions of years ago when they were closer and the universe was younger. But the light they're emitting today, it's already doomed. It will never reach us, no matter how long it travels. These galaxies are visible in our past, but have already disappeared from our future. During the period called cosmic inflation, a mind-bendingly brief moment just after the Big Bang, space expanded far faster than light. In less than a trillionth of a trillionth of a trillionth of a second, the universe grew from subatomic scales to potentially larger than a grapefruit. That's not just faster than light, that's faster than anything we can properly imagine. This superluminal expansion didn't break any laws because, again, it was space itself doing the expanding, not objects moving through space. It's like the difference between running across a field, limited by your speed, and the field itself stretching, no speed limit applies. The universe, it seems, has found a loophole in its own rules. This cosmic loophole has profound implications. It means there are parts of the universe that are causally disconnected from us, regions that we can never influence and that can never influence us. We're not just separated by distance, but by the very structure of space-time itself. It's the ultimate social distancing, enforced by the laws of physics. What's even stranger is that from the perspective of someone in one of those distant, faster-than-light receding galaxies, we're the ones receding faster than light. There's no privileged position, no absolute reference frame. Everyone sees themselves as stationary, while the universe expands around them. It's cosmic democracy in action. Everyone's perspective is equally valid. This also means the observable universe has a hard boundary, not in space but in possibility. There's a sphere around us, currently about 46.5 billion light-years in radius, that represents the absolute limit of what we can ever observe. Beyond that sphere, space is receding so fast that no signal, no information, no causal connection can ever be established. It might as well be another universe entirely. The fact that space can expand faster than light also helps explain one of cosmology's great mysteries. Why is the universe so uniform? If different regions couldn't have communicated since the Big Bang, how do they all have nearly the same temperature and density? The answer: inflation. That period of faster-than-light expansion took tiny regions that were in thermal equilibrium and stretched them across the entire observable universe before they had time to develop differences. It's like taking a small, perfectly mixed cup of coffee and instantly expanding it to the size of a swimming pool. The coffee remains uniformly mixed because the expansion happened faster than the cream could separate from the coffee. That's our universe. a cosmic cup of coffee stretched faster than light itself. When we think about the shape of the universe, our minds immediately go to shapes we know: spheres, cubes, saddles. But the universe doesn't care about our limited imagination. Its shape exists in dimensions and ways that our brains, evolved to navigate Earth's surface, struggle to comprehend. Here's the fundamental question: is the universe flat, curved like a sphere, or curved like a saddle? This isn't asking about local bumps and dips caused by massive objects. This is about the overall, large-scale geometry of space itself. And the answer has profound implications for the ultimate fate of everything. In a flat universe, geometry works the way we learned in school. Parallel lines never meet. Triangles have angles that sum to exactly 180 degrees. If you travel in a straight line, you keep going forever without returning to your starting point. It's infinite, or at least indefinitely large, stretching endlessly in all directions without curving back on itself. In a spherical universe, what cosmologists call positively curved, space curves back on itself like the surface of a balloon. Parallel lines eventually converge. Triangles have angles summing to more than 180 degrees. Travel far enough in a straight line, and you'd eventually return to where you started, like circumnavigating Earth but in 3 dimensions. Such a universe would be finite but without boundaries. No edges, no walls, just space folding back on itself. In a hyperbolic or negatively curved universe, space curves outward like a saddle or a Pringle chip. Parallel lines diverge. Triangles have angles summing to less than 180 degrees. This universe would be infinite, with space stretching out in a way that creates ever more room the farther you go. So which one is our universe? After decades of increasingly precise measurements, especially of the cosmic microwave background, we found something remarkable. The universe appears to be flat, or so close to flat that we can't detect any curvature. The angles of cosmic triangles formed by patterns in the CMB sum to 180 degrees within our measurement precision. This flatness is actually bizarre and requires explanation. Of all the possible curvatures the universe could have, it happens to be balanced on the knife's edge of perfect flatness. It's like randomly throwing a pencil and having it land perfectly balanced on its point. Possible. Yes. Likely. Not without some underlying reason. The theory of cosmic inflation provides that reason. During inflation, any initial curvature would have been stretched out, like inflating a balloon until a small patch looks perfectly flat. We might be living in a curved universe that's so enormous that our observable portion appears flat, like how Earth's surface seems flat to someone standing in a field. But here's where things get philosophically interesting. Even if the universe is flat, that doesn't tell us whether it's infinite. A flat universe could be infinite, stretching forever in all directions. Or it could be finite but with a weird topology, like a 3-dimensional version of a video game screen where going off one edge brings you back on the opposite side. Imagine living in a cosmic version of Pac-Man, where space loops back on itself not through curvature, but through its fundamental topology. You could have a flat, finite universe shaped like a 3-dimensional torus donut, where traveling far enough in any direction brings you back home. We've looked for evidence of this, repeated patterns in the CMB that would indicate we're seeing the same regions from different directions, but haven't found any. Either the universe doesn't loop, or it loops on scales larger than we can observe. The shape of the universe also determines its fate. A positively curved universe would eventually stop expanding and collapse back in a big crunch. A negatively curved or flat universe would expand forever, growing ever colder and more dilute. With dark energy driving accelerated expansion, even a slightly closed universe might expand forever, overcoming the tendency to collapse. Our measurements suggest we're heading for eternal expansion. The universe will keep growing. Galaxies will drift apart, stars will burn out, and eventually, in the unimaginably distant future, even black holes will evaporate. The universe will become a cold, empty, expanding void with nothing but occasional particles separated by distances that dwarf today's observable universe. But that fate is so far in the future, we're talking googles of years, that it's almost meaningless to contemplate. Stars will continue forming for trillions of years. Life has barely begun its potential run in the cosmos. We're still in the universe's morning, with a whole day ahead of us. Let me share something that might help you visualize curved space, even though your brain isn't built for it. You know how a two-dimensional ant on a balloon's surface can't perceive the third dimension the balloon curves through? We're in the same situation, but one dimension up. If our three-dimensional space is curved, it's curving through a fourth spatial dimension we can't directly perceive. This doesn't mean the fourth dimension exists in any physical sense we can access. It's more of a mathematical convenience, a way to describe curvature without requiring an actual higher dimensional space. The universe doesn't need to be embedded in anything to be curved. Curvature can be intrinsic to space itself. Here's my favorite analogy for understanding curved space. Imagine you're playing a video game where the character walks on what seems like a flat surface. But the game is programmed so that walking far enough north brings you to the South Pole. Walking east eventually brings you west. The character experiences a curved space, even though the TV screen is flat. The curvature is in the rules, not in any physical bending you can see. That's how our universe might work. The rules of space, how distances relate, how angles work, how parallel lines behave, could encode curvature without space needing to bend through anything. It's curvature as a property, not as a shape. Scientists have tried to detect this curvature by looking for cosmic triangles. Using the cosmic microwave background, they identify hot and cold spots and measure the angles between them. In a curved universe, these angles wouldn't sum to what we'd expect in flat space. So far, every measurement confirms flatness to incredible precision. But here's a wild thought. What if the universe is curved, but on scales so vast that our entire observable universe is like a tiny patch on an enormous sphere? We'd measure flatness simply because we can't see far enough to detect the curvature. It would be like an ant concluding the Earth is flat because its yard looks level. There's also the possibility of more exotic shapes. The universe could be a Klein bottle, a mathematical surface that passes through itself in 4 dimensions. Or it could have different curvatures in different directions, flat in some ways and curved in others. Mathematics allows for geometries that would make M.C. Escher's head spin. What strikes me most about this cosmic geometry is how it connects the very largest scales to the very smallest. The shape of the entire universe is determined by its total energy content: matter, radiation, dark energy. Add up all the energy in every star, every atom, every quantum field fluctuation, and you get the curvature of space. We're all contributing to the shape of everything. So when you ask about the edge of the universe, you're really asking about its shape. And that shape, as far as we can tell, has no edge at all. Whether flat and infinite or flat and looping, or so slightly curved that we'll never notice, the universe seems determined to avoid boundaries. It's as if existence itself abhors an edge, preferring instead to continue, to curve, to loop, or to stretch forever rather than simply stop. Think about standing on Earth. If you start walking in any direction and keep going perfectly straight, you'll eventually return to where you started. You'll never hit an edge or fall off. Earth's surface is finite. It has a measurable area, but it's unbounded. There's no boundary, no edge, no end of Earth sign. The universe might be the same way, just in 3 dimensions instead of 2. This is a concept that breaks most people's brains the first time they encounter it. So let's build up to it slowly. Start with a circle. It's a one-dimensional curve that loops back on itself. An ant walking along a circle never finds an end. It just keeps going around. The circle is finite. It has a specific circumference, but unbounded, no edges. Now move up to a sphere's surface, a 2-dimensional space that curves back on itself in 3 dimensions. Same principle, finite area, no boundaries. You can travel forever on Earth's surface without finding an edge. The universe could be a three-dimensional version of this, a hypersphere curving through a fourth spatial dimension we can't perceive. If you traveled far enough in any direction in such a universe, you'd eventually loop back to your starting point. The universe would be finite in volume, but have no boundaries, no edges, no walls. This isn't just mathematical speculation. It's a serious scientific possibility that cosmologists have been testing for decades. They look for repeating patterns in the cosmic microwave background that would indicate we're seeing the same regions of space from different directions, like looking around a globe and seeing the back of your own head. So far, no such patterns have been found. Either the universe doesn't loop, or it loops on scales larger than our observable universe. We might be living in a cosmic sphere so vast that our observable universe is like a microscopic patch on its surface, too small to detect any curvature. But spheres aren't the only way to have finite, unbounded space. Remember Pac-Man? When Pac-Man goes off the right edge of the screen, he reappears on the left. Go off the top, come back at the bottom. The game space is finite but has no boundaries. It wraps around in a way that's different from a sphere. Mathematicians call this a toroidal topology, basically a fancy way of saying donut-shaped, though in 3 dimensions it's harder to visualize. The universe could have this kind of wraparound structure, where space connects back to itself without curving. You'd still have no edges, but the geometry would be fundamentally different from a sphere. There are even more exotic possibilities. The universe could be shaped like a Klein bottle, a surface that passes through itself in 4 dimensions. Or it could have a completely irregular topology that doesn't correspond to any simple shape we can imagine. The key insight is that finite doesn't require bounded. The universe can be limited in size without having edges. This resolves a philosophical problem that's bothered thinkers for millennia. If the universe has an edge, what's beyond it? The answer might be that there is no edge to be beyond. This edgeless quality of space might be more than just geometric. It might be fundamental to the nature of existence itself. Consider this: every edge we encounter in daily life is really just a boundary between 2 things. The edge of a table is where table meets air. The shore is where land meets sea. But what would be beyond the edge of everything? By definition, nothing, and not even the kind of nothing that's actually something like empty space, but true philosophical nothingness, which might not even be possible to define coherently. Perhaps edges can only exist within space, not of space itself. Perhaps the universe, by its very nature, must be either infinite or unbounded. An edge would require something beyond the edge, which would mean the universe hadn't really ended there after all. There's something deeply satisfying about a universe without edges. It means you could explore forever without hitting a wall. It means there's no privileged boundary, no cosmic fence separating existence from non-existence. Every point in space is equivalent to every other point. None is closer to an edge because there is no edge to be close to. But it's also unsettling. Humans like boundaries. They help us organize, categorize, understand. A universe without edges is a universe that can't be fully mapped, can't be completely explored, can't be definitively bounded. It's a universe that remains fundamentally mysterious no matter how much we learn about it. Perhaps that's the real lesson here. The universe doesn't conform to our expectations or preferences. It doesn't care that we evolved to think in terms of edges and boundaries. It simply is what it is, and what it is might be edgeless, boundless, infinite in possibility if not in extent. Imagine a photograph of the universe when it was just 380,000 years old, a cosmic baby picture, if you will. That's essentially what we have with a cosmic microwave background. It's not just the oldest light we can see. It's the oldest light it's possible to see, a fossil from when the universe first became transparent. Before this moment, the universe was opaque. Photons couldn't travel far without bumping into electrons, like trying to shine a flashlight through milk. The universe was a hot, dense soup where light was trapped, constantly scattering, never free to stream across space. Then, 380,000 years after the Big Bang, something magical happened. The universe had cooled enough for electrons and protons to combine into hydrogen atoms. Suddenly, light was free. The cosmic fog lifted, and photons that had been bouncing around since the beginning could finally travel unimpeded. They've been traveling ever since. That ancient light is still with us. It fills the universe, passes through your body, streams through your walls. About 400 photons from the Big Bang pass through every cubic centimeter of space every second. You're swimming in ancient light, bathed in the afterglow of creation itself. We can't see this light with our eyes. It's been stretched by the expansion of space from visible light into microwaves. But with the right instruments, we can detect it, map it, study it in exquisite detail. And what a story it tells. The CMB was discovered by accident in 1964. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a large horn antenna for radio astronomy. But they kept detecting an annoying background hiss no matter where they pointed their antenna. They tried everything to eliminate it, cooling their equipment, removing pigeon droppings from the antenna, yes, really, rebuilding components. Nothing worked. The hiss persisted. What they'd stumbled upon was the echo of the Big Bang itself. That cosmic static they couldn't eliminate was the cooled remnant of the universe's first light, stretched and dimmed by billions of years of cosmic expansion, but still detectable, still carrying information from the dawn of time. The CMB isn't uniform. It has tiny variations, regions slightly warmer or cooler by just a few parts in 100,000. These microscopic differences are the seeds of everything we see today. Slightly denser regions had slightly stronger gravity, pulling in more matter, eventually forming the first stars and galaxies. The grand structures of the universe, galaxy clusters, cosmic voids, the vast web of matter stretching across space, all grew from these quantum fluctuations in the infant universe. It's like looking at a baby's DNA and seeing the adult they'll become. Those tiny temperature variations in the CMB encoded the future history of the universe. Every galaxy, every star, every planet traces its origin back to these primordial ripples. Modern satellites have mapped the CMB in stunning detail. The patterns in this ancient light tell us the universe is 13.8 billion years old, that it's geometrically flat, that contains about 5 ordinary matter, 27 dark matter, and 68 dark energy. It's like finding a cosmic recipe card, written in light itself. But here's what really amazes me. The CMB is remarkably uniform. Regions of space that should never have been in contact, separated by distances greater than light could have traveled since the Big Bang, have nearly identical temperatures. How is this possible? The answer is cosmic inflation. In the first fraction of a second after the Big Bang, space expanded faster than light. Remember, space itself can do that, taking regions that were once in thermal contact and stretching them across the entire observable universe. It's like taking a tiny drop of well-mixed paint and instantly spreading it across a vast canvas. The color remains uniform because the spreading happened faster than any variations could develop. The CMB also carries subtle patterns called acoustic oscillations, frozen sound waves from when the universe was young. Before atoms formed, the universe was filled with a hot plasma where sound waves could travel. These waves compressed and rarefied the plasma, creating patterns of density that we can still see in the CMB and in the distribution of galaxies today. Think about that. We can detect sound waves from when the universe was less than 400,000 years old. Not hear them, they're far below any frequency we could perceive, but see their frozen patterns written across the sky. The universe sang in its infancy, and the song is still visible. The CMB is also the most perfect blackbody spectrum ever measured. A blackbody is an idealized object that absorbs and emits radiation perfectly, and its spectrum has a very specific shape that depends only on temperature. The CMB matches this theoretical shape to incredible precision, better than 1 part in 100,000. It's nature's way of showing us that the early universe was in perfect thermal equilibrium. There's something profound about detecting this ancient light. Every photon in the CMB has been traveling for 13.8 billion years, carrying information about the universe when it was younger than many stars are today. These photons have crossed billions of light years, passed through galaxies, survived encounters with cosmic dust and magnetic fields, all to deliver their message to our detectors. And what a message it is! The CMB tells us we live in a universe that began hot and dense, expanded and cooled, and somehow developed the right conditions for atoms, stars, planets, and life. It confirms our theoretical models while also revealing mysteries, like why there's more matter than antimatter, or what exactly dark matter and dark energy are. The CMB is also our cosmic horizon in time. We can't see light from before this moment because the universe was opaque. It's like trying to see through a wall. No matter how good your telescope, you can't see what's on the other side. The CMB is our wall, our limit, our earliest glimpse of the cosmos. But even this wall carries information about what came before. The patterns in the CMB were set by events in the universe's first fraction of a second, quantum fluctuations during inflation that were stretched to cosmic scales. By studying these patterns, we can infer what happened in epochs we can never observe directly. In a sense, the CMB is the universe's autobiography, written when it was young but readable only now that we've developed the tools to detect it. It's a message from the past that took most of cosmic history to deliver, arriving just in time for a species curious enough to decode it. Now let's venture into territory where even physicists start to feel uncomfortable. The wild frontiers of theoretical cosmology, where equations meet imagination and produce offspring that would make science fiction writers jealous. What if our universe is just a three-dimensional surface floating in higher dimensional space? This isn't New Age mysticism. It's a serious proposal from string theory called the brain world scenario. In this picture, we're trapped on a three-dimensional brain, short for membrane, embedded in a higher dimensional bulk. Think of it like this. Imagine beings that live entirely on a sheet of paper. They can move north-south and east-west but have no concept of up or down. To them, the universe is two-dimensional. But that paper exists in our three-dimensional space. We could have multiple sheets stacked together, each one a separate two-dimensional universe, invisible to the others except through gravity, which might leak between sheets. Scale that up a dimension, and you have our situation. We might be living on a three-dimensional brain in a 4 or 5 or 11-dimensional space. Other brains, other universes could be floating nearby, maybe just millimeters away in the extra dimensions, but completely inaccessible to us because we're confined to our brain. This isn't just mathematical speculation. It could explain why gravity is so much weaker than the other forces. Maybe gravity spreads out into the extra dimensions while other forces are stuck on our brain. It's like sound from a radio spreading through a room while the radio itself stays in one place. Some versions of this theory suggest that the Big Bang was actually a collision between two brains. Imagine two sheets of paper drifting through space, occasionally bumping into each other. Each collision would appear to beings on the sheets as a Big Bang, a moment of incredible energy appearing everywhere at once. The universes would then drift apart until they collide again, creating cyclic cosmology where Big Bangs happen repeatedly. Then there's the holographic principle, perhaps the strangest idea in modern physics. It suggests that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface at the boundary of space. We're not living in a simulation, we're living in something even weirder, a universe where the number of dimensions depends on how you look at it. This comes from studying black holes. Stephen Hawking and others discovered that the information content of a black hole is proportional to its surface area, not its volume. That's bizarre. It's like saying a library's information capacity depends on the size of its walls, not how many shelves fit inside. If this principle applies to the universe as a whole, then everything we experience as three-dimensional reality might be equivalent to information encoded on a distant two-dimensional surface. We're like shadows cast by a more fundamental reality, except the shadows have convinced themselves they're the real thing. Consider domain walls, boundaries in space where the laws of physics might change. In the early universe, as fields settled into their current values, different regions might have chosen different ground states. Where these regions meet, you'd have domain walls, cosmic defects where physics itself has a discontinuity. Walking through a domain wall might be subtle. Maybe electrons would have slightly different mass, or the strong force would be a bit stronger. Or it might be dramatic, matter might not be stable, or chemistry might work differently. These walls, if they exist, would be the closest thing to an actual edge the universe might have, not an edge of space, but an edge between different physics. There's also Gödel's rotating universe, proposed by the same Kurt Gödel, who broke mathematics with his incompleteness theorems. He found a solution to Einstein's equations describing a universe that rotates as a whole. In such a universe, space and time get mixed up in strange ways. Travel far enough in space, and you could arrive before you left. The entire universe becomes a time machine. We know our universe isn't rotating in Gödel's way. We'd see specific patterns in the CMB if it were. But the fact that Einstein's equations allow such a solution reminds us that the universe is under no obligation to match our intuitions about what's possible or sensible. What about white holes, the theoretical opposite of black holes? While black holes let nothing escape, white holes would let nothing enter. They'd spew matter and energy into the universe, possibly appearing as Big Bang-like events. Some physicists have speculated that our Big Bang might have been a white hole, though this raises more questions than it answers. Or consider cosmic strings, not the tiny strings of string theory, but massive one-dimensional defects in space-time that might stretch across the universe. These would be thinner than an atom, but so dense that a kilometer of cosmic string would weigh as much as Earth. They'd bend space around them, creating gravitational lenses that could produce duplicate images of distant galaxies. If cosmic strings exist, they'd be like edges within space, not boundaries but discontinuities, places where space itself has a kind of scar from the universe's violent birth. They might oscillate, generating gravitational waves we could potentially detect. They might even form loops that collapse into black holes. There's the multiverse, not just one flavor, but many. The quantum multiverse where every possibility plays out. The inflationary multiverse where bubble universes constantly form. The string theory landscape where different universes have different physical laws. The mathematical multiverse where every consistent mathematical structure exists as a physical reality. In some of these scenarios, our universe might have edges where it meets other universes. Not edges in space, but edges in reality itself, boundaries between different ways physics could work. These edges might be impossible to cross, or crossing them might fundamentally change what you are. Perhaps most mind-bending is the idea that the universe might be emergent, that space, time, and even the laws of physics might not be fundamental, but arise from something deeper. Just as temperature emerges from the motion of atoms, space-time might emerge from more fundamental entities we haven't discovered yet. In this view, asking about the edge of the universe is like asking about the edge of temperature. The question assumes space is fundamental when it might be just a useful approximation of something far stranger. These ideas remind us that the universe is not obligated to be simple, sensible, or satisfying to human minds. It might have edges we can't see, boundaries we can't cross, dimensions we can't perceive. Or it might be even stranger, a reality where the very concept of edge is meaningless, like asking what's north of the North Pole, or what happened before time began. The multiverse hypothesis is perhaps the most audacious idea in modern cosmology. It suggests our universe, everything we can see, everything we'll ever be able to see, is just one of many, perhaps infinitely many universes, each with its own laws, its own history, its own story. This isn't mysticism or science fiction. It's a serious scientific proposal that emerges naturally from our best theories of cosmology and quantum mechanics. Though I should be clear, there's no direct evidence for other universes. We can't see them, visit them, or receive signals from them. The multiverse remains a hypothesis, a framework for thinking about reality that might or might not be correct. The simplest multiverse concept comes from cosmic inflation. During inflation, space expanded exponentially fast. But inflation might not have happened uniformly everywhere. In some regions, it might have ended sooner, creating bubble universes within the inflating space. Each bubble would be a separate universe with its own properties. Picture a pot of boiling water. Bubbles form randomly, each one a pocket of steam in the liquid. Now imagine the water is expanding space, and the bubbles are universes. New bubbles constantly form while existing ones grow. The result is an infinite froth of universes, forever multiplying, forever separated by inflating space. In this eternal inflation scenario, our universe is just one bubble among countless others. Some bubbles might have different physical constants, stronger gravity, weaker nuclear forces, different numbers of dimensions. Most would be sterile, unable to support complexity. But some, like ours, would have conditions just right for stars, planet, and life. This could explain one of cosmology's great mysteries. Why are the constants of nature so perfectly tuned for complexity? If gravity were slightly stronger, stars would burn out too quickly. Slightly weaker, and they'd never ignite. The same fine-tuning appears everywhere, in the strength of forces, the masses of particles, the rate of cosmic expansion. In a multiverse, this fine-tuning isn't mysterious. With enough universes trying different combinations, some will randomly hit upon values that work. We find ourselves in such a universe not because it was designed for us, but because we couldn't exist anywhere else. It's the ultimate selection effect. We observe a universe compatible with observers because we are observers. Then there's the quantum multiverse, arising from the many worlds interpretation of quantum mechanics. Every time a quantum event has multiple possible outcomes, which happens countless times every second, reality splits. Each outcome happens in its own branch of the quantum multiverse. In one branch, that radioactive atom decayed. In another, it didn't. In one branch, you continued reading this sentence. In another, you stopped to check your phone. Every possible history plays out in its own branch, creating an incomprehensibly vast tree of realities, all equally real, all forever isolated from each other. This isn't speculation, it's one way to interpret the mathematics of quantum mechanics. The equations don't pick a single outcome, they describe all possible outcomes simultaneously. The many worlds interpretation says all those outcomes actually happen, just in separate branches we can't perceive. The string theory landscape offers yet another multiverse. String theory suggests that extra dimensions beyond our familiar three might be compactified, curled up too small to see. But there might be many ways to curl them up, perhaps 500 different ways or more. Each way would create a universe with different physics. Imagine you're looking at a garden hose from far away. It looks one-dimensional, just a line. But up close, you see it has a circular cross-section. An ant on the hose could go along its length or around its circumference. The extra dimension was always there. It was just too small to see from a distance. String theory suggests our universe might have 6 or 7 extra dimensions, all curled up smaller than atoms. The way they're curled determines the laws of physics we observe. Different universes would have different compactifications, leading to different physics, different particles, forces, even different numbers of large dimensions. Max Tegmark has proposed the ultimate multiverse, the mathematical multiverse. He suggests that every mathematically consistent structure exists as a physical reality. Not just universes with different physics, but universes with different mathematics, where 2 plus 2 might equal 5, where logic itself works differently. This is the most expansive multiverse concept imaginable. It includes not just variations on our universe, but utterly alien realities we can't even conceive. Universes with different numbers of time dimensions. Universes where cause doesn't precede effect. Universes governed by mathematics we haven't discovered and couldn't understand if we did. The multiverse hypothesis faces serious criticism. How can we test something we can't observe? Isn't a theory that explains everything by invoking infinite, unseen universes just giving up on explanation? These are valid concerns that divide the physics community. Some argue the multiverse is a prediction, not an assumption. If our best theories naturally lead to multiple universes, shouldn't we take that seriously? Others counter that science requires testability, and untestable predictions aren't really predictions at all. There might be indirect ways to test multiverse theories. Collisions between bubble universes might leave marks in the cosmic microwave background. The particular constants of nature we observe might show statistical patterns expected from random selection. Quantum experiments might reveal subtle influences from parallel branches. So far, no smoking gun has been found. The CMB shows no clear evidence of bubble collisions. The constants of nature don't show obvious statistical patterns. Quantum experiments haven't detected parallel branches. The multiverse remains a possibility, not a discovery. But here's what captivates me. Even considering the multiverse expands our conception of reality. It suggests existence might be far grander than we imagined. That our universe, vast as it is, might be a mote in an infinite sea of possibilities. If the multiverse exists, it means every possible story plays out somewhere. Every variation on your life, every alternative history, every dream and nightmare. All real, all happening in universes you'll never see. It's simultaneously humbling and elevating. We're infinitely small in the grand scheme, yet part of something infinitely creative. Even if the multiverse doesn't exist, the fact that our equations suggest it tells us something profound. Reality is stranger than we imagined and might be stranger than we can imagine. The universe, or multiverse, doesn't care about our cognitive limitations. It simply is what it is, vast and weird and wonderful. After all this wandering through dimensions and infinities, through quantum possibilities and cosmic edges that aren't really edges, we return to where we started. That simple, almost childlike question, where does space stop? And the answer, if we can call it an answer, is beautifully ambiguous. Space might not stop at all. It might go on forever, an infinite expanse without boundary or end. Or it might curve back on itself, finite but edgeless, like the surface of a sphere, but in 3 dimensions our minds struggle to picture. It might be one of many spaces, nested in higher dimensions or branching in quantum superposition or floating in an inflating foam of other universes. We've discovered that the question itself might be wrong. Asking where space stops assumes space is the kind of thing that could stop, like a road or a story. But space might be more fundamental than that, more subtle. It might be the stage on which reality plays out, unable to have an edge because an edge would require something beyond the edge, and beyond space there might be nothing, not even the nothing we can imagine, but a true absence that has no properties, no existence, no meaning. What we do know is that our observable universe has limits, not edges but horizons. Light from beyond 46.5 billion light-years away hasn't had time to reach us. Galaxies are disappearing beyond the cosmic event horizon, racing away faster than light can chase them. We live in a bubble of visibility, forever surrounded by the unknowable. We know space is expanding, has been expanding since the beginning, and is now expanding faster and faster. We know it can curve and stretch and carry galaxies apart faster than light. We know it's not empty but seething with quantum energy, with virtual particles appearing and disappearing, with fields that give rise to everything we see and everything we are. We know the universe began in a hot, dense state 13.8 billion years ago. not a point in space, but everywhere in space simultaneously. We know it cooled and expanded, formed atoms and stars and galaxies, created the conditions for planets and chemistry and life. We know all this from ancient light, from the cosmic microwave background that still whispers the universe's origin story in every cubic centimeter of space. But for all we know, the mysteries multiply. What is dark matter? What is dark energy? Why is there something rather than nothing? Did anything exist before the Big Bang? Are there other universes? Is reality fundamental or emergent? Why these laws of physics and not others? Why does the universe seem so perfectly tuned for complexity and life? These aren't just gaps in our knowledge, they're chasms. We've mapped the cosmic web, measured the universe's age to remarkable precision, detected gravitational waves from colliding black holes. Yet we don't know what 95% of the universe is made of. That bends under the pull of gravity and the curvature of space itself. That's why huge objects like stars and black holes can bend light, a phenomenon known as gravitational lensing. So when we gaze out at the night sky, we're not just seeing objects spread around flat, empty space. We're seeing a web of light moving through curved space, stretched and bent and sculpted by the mass of everything around it. It's like looking at the stars through a slow-moving funhouse mirror. Only the distortions tell us something accurate about the form of the cosmos. Now let's return to our balloon one last time. As it inflates, the distances between the galaxies on its surface rise. But the galaxies themselves don't expand. They stay the same size. That's because the expansion of space happens on huge scales between objects not gravitationally bound together. So our Milky Way, our solar system, even our planet and its crusty old coffee shops, none of things are getting stretched like taffy. The expansion only takes hold in the huge space between galaxies. And what's fueling this expansion? Well, we now believe that dark energy, a mystery kind of energy inherent to space itself, is pushing the universe to accelerate in its growth. It's like the balloon is not simply inflating, but doing so faster and faster with every breath. We don't know exactly what dark energy is, but we can detect its effects in the way distant galaxies move and how old light spreads across the sky. So where does this leave us? It means we exist in a space that might be curved, that might be finite yet boundless, expanding yet centerless, shaped by rules that defy our everyday experience yet make perfect sense in the big cosmic dance. In all of this, the curves, the expansion, the possibility of looping back to our starting place, can be imagined with a simple balloon, a rubbery metaphor floating across thinking space, whispering ancient truths about a universe that grows not outward from anything, but inside itself. Next time you see a balloon floating into the sky, give it a little nod. It may be full of helium and squeaky good fun, but it also holds within it the outline of something much greater. A gentle curve, a length of space, and the calm sense that maybe, just maybe, the place you're headed is also the location you started. Only now you've traveled the universe to get there. Infinity. The word itself feels like it should reverberate when you speak it. It's big, strange, and more than a bit terrifying. It brings up ideas of boundless stars, limitless space, and the kind of math problems that make high school students reassess their life choices. But what does it actually mean when we ask, is the universe infinite? Is space actually limitless, expanding on forever without a final border or wall? Or is there anything more subtle going on? Let's start with what we know. So far, everything we've measured about the big-scale structure of the universe suggests that it might be limitless. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, demonstrate that space is extremely close to being flat, not rough like a sphere and not curved like a saddle, but flat in a geometrical sense. And in the framework of general relativity, a flat universe could very well be endless. If it isn't, it's at least much, much larger than the portion we can witness. That takes us to the observable world, the cosmic bubble we can see. It stretches around 93 billion light-year wide. That's the part of the universe we have access to since light from those locations has had time to reach us since the beginning of the cosmos. But beyond that, it might keep going. There might be galaxies upon galaxies, cosmic structures we'll never detect, vast regions of space that are forever beyond our view. And here's the issue: we can't actually establish or refute whether the cosmos is infinite since we are constrained to our observational boundaries. We're like ants on a seashore gazing in every direction and seeing only sand. For all we know, the beach spans across the continent. Or maybe it terminates a few dunes over in a tide pool full of curious crabs. We just can't see far enough to know. This raises an important point. We don't measure infinity the way we measure, say, the distance to the moon. You can't stick a ruler on space and keep going till the numbers run out. Infinity isn't a number. It's an idea, a notion. And in science, notions need evidence. That's when it gets complicated. You can never directly witness infinity. You may only seek for indicators that space shows no signs of curving back on itself, or ending abruptly, or acting in a way that signals it loops. So far, we've looked in all directions and seen no detectable edge, no precipitous drop-off, no cosmic fence with a do not pass sign hanging on it. But that doesn't mean such a thing doesn't exist. It just means it's beyond what we can see. And unless we suddenly discover a telescope that can break the speed of light and outpace the expansion of the cosmos, that's not likely to change anytime soon. The idea of an infinite world brings with it some rather odd ramifications. If space is indeed infinite, then the amount of matter it contains is also likely infinite, or at least so staggeringly huge that it might as well be. That means an endless number of stars, planets, comets, clouds of dust, and yes, maybe even life. Somewhere out there in the farthest reaches of a never-ending galaxy, there might be another planet much like Earth. Maybe it has trees that grow sideways or waters that shine with weird colors. Maybe it has species asking the same questions we are, wondering whether their universe ever stops. And here's where it starts to bend the brain a little. In an infinite world, if matter is dispersed more or less uniformly, then the principles of probability predict that patterns will ultimately reoccur. Which means that somewhere out there could be a version of you or several. Some may be practically identical. Others might have chosen a different breakfast cereal this morning and accidentally altered the direction of their entire day. Now, don't worry. This isn't meant to be unsettling. You're not likely to bump into your cosmic twin at the grocery store. These areas are potentially so far away that they are forever unreachable. The light from those portions of space will never ever reach us, even if we wait longer than the duration of the universe multiplied by every grain of sand on Earth. Still, the implications are substantial. Infinity isn't merely an issue of size. It's a shift in thinking. It transforms the universe from something enormous to something endless. You no longer have to wonder what's beyond the edge of the map because there is no edge, just more map forever. Of course, there are excellent scientific reasons to be careful about assuming the cosmos is limitless. We have just a finite sample to work with. And cosmologists remain open to the idea that space might be immensely big but nonetheless finite. It could curl gently back on itself in a way we can't yet detect, looping into higher dimensions or generating a shape more exotic than we've ever imagined. There's also the question of time. The universe might be boundless in space but finite in duration. It had a beginning, what we call the Big Bang. And while the notion of a beginning is inherently tricky, it suggests that even if the cosmos is boundless in length, it has not always existed in its current form. Philosophically, infinity challenges the way we relate to the universe. Most things in our daily lives have boundaries. Our time, our energy, the amount of cookies in the jar. Infinity breaks that mold. It removes the boundaries and offers up a playground of unlimited possibility that can be uplifting or overpowering, or both at the same time. Some ancient thinkers were very concerned with the idea of infinity. Aristotle, for example, believed the universe must be finite because actual infinities were just too odd to grasp. And even today, some scientists and philosophers question whether true infinities can exist in the real world or whether they're just handy abstractions. But whether or not the world is endless, pondering it has worth. It stretches the intellect, inspires humility, and reminds us how narrow our perspective really is. When you stare up at the stars, you're staring into a mystery so immense that even our boldest measurements barely scrape the surface. You're seeing simply a local glow, a few lights in the window of the cosmic mansion. And yet, here we are, little animals on a spinning globe, wondering how far space goes. We develop tools to hunt old light. We invent math to frame the impossible. And we lie awake at night worrying about what is beyond the final star we can see. Maybe the universe is limitless. Maybe it's not. Either way, it's more than enough. More than enough to fuel our inquiries, our stories, our research, and our hopes. More than enough to remind us that we're part of something genuinely vast. And the most lovely aspect of all, you don't have to know how far it goes to feel at home in it. You're already entwined into its fabric. A flash of idea on the edge of the observable, flickering faintly in a cosmos that may never end. There's something enticing about the concept of an edge. We grow up with edges, walls, fences, sidewalks, lunchboxes. Everything we encounter seems to halt somewhere. So when we think about the universe, it's only logical to suppose it must stop too. Surely, after some truly astonishing distance, space must come to an end, like the final chamber in a very enormous home or the edge of a massive tablecloth dangling over the abyss. But here's the twist. Space doesn't actually need an edge. It can be finite in size without having a boundary at all. And that's where things get beautifully odd. Let's start with something easy. Picture the surface of the Earth. If you were to walk in a straight line in any direction, you would eventually circle back to where you started. You wouldn't tumble off anything. You wouldn't strike a wall. And you wouldn't find a signpost reading End of Earth. Please turn around. The surface is limited but limitless. It loops back on itself in a smooth fashion. Now take that notion and expand it to a three-dimensional space. Imagine living inside a volume of space that wraps around itself in much the same way the surface of a globe does in 2 dimensions. If you could keep traveling forward in a perfectly straight line through this space, you might finally return to your starting location, having never encountered a wall, cliff, or any type of edge. This kind of space is not science fiction. It's a totally acceptable model in cosmology. It's called a finite unbounded space. It sounds like a paradox at first, like stating a cup can be full of tea but not contain any liquid. But if you comprehend the geometry, it clicks into place. Space can be shaped in such a way that it closes in on itself, generating a complete volume without ever needing to terminate. One among the classic forms used to represent this principle is the torus. Imagine a donut. Not the jelly-filled sort, but the smooth, spherical sort with a hole in the middle. The surface of the donut is 2-dimensional. You can stroll around it without leaving the surface, but it has no borders. It loops back on itself both horizontally and vertically. If you're an ant walking on the donut, you can travel endlessly without ever striking a boundary. Now imagine a 3-dimensional version of that where space loops in many directions. This doesn't suggest the universe is shaped like a pie, but the torus helps us grasp how space might act if it were finite and without a border. You could start at one point in space, travel in a straight path, and after a very, very long period, find yourself right back where you began, like a galactic boomerang. Another helpful example comes from video games. In certain old arcade games like Pac-Man or Asteroids, if you move your character off the edge of the screen on one side, they resurface on the opposite side. It's not that there's an unseen tunnel. They've just looped around on a map that spirals back on itself. These are two-dimensional variations of a two-idle space. The gaming environment is finite in size, although the edges don't behave like real-world walls. They link. In theoretical cosmology, this idea is more than just playful musing. Some models imply that the cosmos could have a topology, its basic form that loops back in subtle ways. We might not detect these loops unless we glance far enough and in precisely the proper direction. There's even been talk that if the universe is small and curved just so, we might detect repeated patterns in the cosmic microwave background, like mirrored wallpaper left behind from the Big Bang. So far, we haven't identified any concrete traces of this repeating, but the idea hasn't been ruled out totally. The fundamental fact is that the universe doesn't need an exterior surface or a surrounding emptiness. That's a very human way to look at space. There's something sitting inside something else. But space isn't a thing enmeshed in a bigger item. It is the thing. It's not like a balloon floating in air. It's more like the full balloon itself, with all of us locked on its surface, unable to step outside and gaze in. Even if the cosmos is limitless, it still doesn't require an edge. Infinity isn't a place. It's a property. Saying the universe is limitless is like saying numbers never stop. You don't need to find the last number to know that one doesn't exist. Likewise, you don't need to pinpoint the border of space to know there might not be one. Edges also create philosophical headaches. If there were an edge, what would be beyond it? More space? Something else entirely? A blank void that lies awkwardly waiting to be defined? The moment you introduce an edge, you introduce a paradox. If there's something beyond, then space hasn't really ended. And if there's actually nothing, then how can it be claimed to exist at all? By comparison, the universe without edges avoids this confusion totally. It just is. You can keep moving forever or may come full circle. There's no edge to fall over, no cosmic warning signs, and no need to identify what's beyond the beyond. This doesn't mean we'll never stop questioning about boundaries. Our minds are wired to think in terms of containers. We like beginnings, middles, and ends. But the universe doesn't appear to care much for our mental filing drawers. It stretches, curves, and possibly loops, all without presenting a crisp border to sign off on. Interestingly, even if space has no edges, time might. Our cosmos has a beginning, at least from our perspective, with a Great Bang roughly 13.8 billion years ago. That's not a point in space, but a point in time, a moment when space itself begun spreading from an earlier state. Asking what came before the Big Bang is like wondering what's north of the North Pole. It's not that the question is pointless. It's that our regular coordinates stop operating. All of this offers an image of a cosmos that's considerably more subtle and odd than a huge box. It's not an object you can open the lid on or peek around the edge of. It's more like a melody that plays itself onward, winding around dimensions and humming through time with no ultimate note, no ending chord, only an unending variation. And in that melody, there are no harsh edges, only connections, curves, and continuations. Whether it loops or stretches indefinitely, the universe doesn't close off like a room. It opens up like an idea, not limited by walls, but shaped by relationships. Gravity, light, motion, time. Thus, if you've ever pictured a spaceship going confidently toward the edge of the universe, envision this instead. A lengthy, peaceful voyage that never finds a cliff. Only more stars, more mysteries, and more space. Not because the world extends on forever necessarily, but because it never had an edge to begin with. Before there were stars, before there were galaxies, even before atoms had really settled into their jobs, there was a glow, a soft, homogeneous light diffused throughout the universe like a warm fog, reaching in every direction. It wasn't a spotlight or a flashbulb or a fireworks extravaganza. It was softer than that, gentler, like the first rays of dawn pouring through a window before anyone's had a chance to open their eyes. And part of that brightness is still with us now. We name it the Cosmic Microwave Background, or CMBB for short. It's not simply the oldest light we can see. It's the oldest light anyone can see. A whisper from the very early universe, still drifting slowly into space, passing through galaxies, stars, planets, and sometimes with the correct sensors into our detectors. To understand where this light comes from, let's go back in time, way back. About 13.88 billion years ago, the universe began in a hot, dense state, a singularity of sting energy and unfathomable temperature. In its initial seconds, space expanded fast, spreading out the energy like batter in a skillet. As the universe grew, it cooled, not rapidly, but progressively, like a cosmic pot carefully pulled off the stove. At start, the universe was a blazing soup of particles and radiation. Photons, the particles of light, bouncing around ceaselessly, caught in a fog of charged particles. Electrons and protons zipped around individually, and light couldn't reach very far before being scattered in a new direction. Imagine trying to beam a flashlight through a dense cloud. That's what the cosmos was like during its first few hundred years. Opaque, turbulent, and full of restless action. But then something spectacular happened. About 380,000 years after the Big Bang, the cosmos cooled enough for protons and electrons to unite into neutral hydrogen atoms. This time is poetically called recombination, and it changed everything. With fewer charged particles to scatter off, light was unexpectedly free to travel. The fog lifted. The universe became transparent, and the first light broke loose. That old light released loose over the cosmos has been traveling ever since. It fills the universe in every direction, stretched out by billions of years of cosmic expansion. Once a blistering flash of ultraviolet energy, it's now cooled to a faint microwave hum, a whisper instead of a roar. But it's still there all around us, going into your chamber this very moment like a delicate invisible breeze from the beginning of time. We originally discovered the CMB practically by accident. In the 1960s, two radio astronomers named Arno Penzias and Robert Wilson were using a huge horn-shaped antenna to investigate radio transmissions. They kept detecting a continuous background noise where they pointed their antenna. They cleaned the equipment, double-verified their math, and even deleted some pigeons nesting in the device just in case it was their fault. But the noise remained steady, uniform, and weirdly cosmic. What they had stumbled upon without understanding it at first was the afterglow of the Big Bang. It was the cosmic microwave background, predicted by theory, and now detected in all its nuanced brilliance. That slight hiss on their radio signal turned out to be a window into the young world. Since then, scientists have mapped the CMB in incredible detail. Space missions including COVE, WMAP, and most recently the Planck satellite have provided us a high-resolution picture of this ancient light. And what they revealed is more than simply a glimmer. It's a cosmic blueprint, a snapshot of the universe when it was less than 500,000 years old. At first glance, the CMBB seems amazingly uniform. The same temperature and brightness no matter which way you look. But zoom very closely, and you'll see small fluctuations. Little heated and cool patches barely a few millionths of a degree different from each other. These gentle ripples aren't imperfections. They're the seeds of everything. Tiny changes in density that over billions of years would evolve into stars, galaxies, and eventually you sitting here listening to a video about the universe in your favorite jammies. Those tiny variances are indications. They tell us how matter was dispersed in the early universe. They reveal the physics of the cosmos at its start, and they let us test theories regarding how space and time unfolded in the initial few heartbeats of creation. Even the shape of the cosmos imprints its fingerprints on the CMBB. If space were bent like a spherical or saddle-shaped or flat as a pancake, those geometries would subtly alter the way light moves across space. By evaluating the size and dispersion of the fluctuations in the CMB, physicists can infer the big-scale structure of space itself. And so far, all indicators lead to a universe that is flat, at least within the confines of what we can witness. It's a bit like looking at the pattern of waves on a pond to figure out the form of the shoreline. The way the waves extend and move provides information about the environment they travel through. In the same way, the CMBB conveys encoded signals regarding the shape, size, and ingredients of the universe. Its light is data, photons as historians, and there's something incredibly relaxing about envisioning that shine, a smooth, gentle wash of ancient light, not dazzling or burning, but serene and even. Not one that you can see with your eyes, but one that's always present. It's like the universe's own lobby still playing after all these years. If you could tune in with the correct kind of radio, you'd hear it everywhere. Not as a song, but as a subtle static warmth, a continual low-level presence embedded into the very fabric of space. It's the closest thing the universe has to a baby photo, an image of its first moment of clarity. And it's still whispering to us long after the stars were formed. Long after galaxies whirled into shape, long after Earth began its stately dance around the sun. That light has outlived generations of stars, crossed immeasurable distances, and landed here in your lifetime, ready to tell its story. In a universe filled with mystery, the CMBB is something substantial, something we can measure, map, and comprehend. It reminds us that we don't need to chase the borders of space to discover about its genesis. Sometimes the solutions are already floating all around us, waiting patiently in the glow. So the next time you look up at the night sky, try to visualize it not as black and vacant, but filled with an antique light too dim to discern. It's been traveling for nearly 13 billion years, stretching with every passing moment, bearing the peaceful history of everything. And even now, in the quiet of space, it continues to shine. Is there a true edge to the universe, a last frontier, a cosmic veil, some final border where space just stops? It's a question something continues coming up, not only in science fiction, but in real scientific circles, whispered between chalkboards and telescopes. While conventional cosmology leans toward a world with no hard edge, some speculative theories and thought exercises nudge open the door to weirder possibilities, areas where boundaries might exist, even if we can't exactly see or feel them. Let's start softly with a thought that our three-dimensional cosmos could be a kind of surface or brain floating in a higher dimensional space. This is one of the basic notions in brain cosmology, a branch of string theory. In this concept, our world might be a giant three-dimensional membrane, short for brain, existing within a higher dimensional bulk. We are constrained to this brain. All the particles and forces we know save gravity are stuck here like bugs trapped on a soap bubble. Gravity, being a bit more adventurous, might leak into the surrounding dimensions, which is one reason some physicists say it seems so feeble compared to the other forces. If this theory is right, then our cosmos could have an edge not in three-dimensional space, but in a higher dimensional mass we can't perceive directly. You may envision the brain having a limit or border in the dimensions we don't perceive. From our point of view, everything seems continuous and edge-free. But from the perspective of a hypothetical five-dimensional entity with supervision, we might look like a cosmic disk with boundaries at the rim. It's a little frightening to think about being watched by something with more dimensions than we can fathom, but comfortable too. We'd be the strange mystery to them. Then there's the idea of cosmic domain borders, boundaries between distinct regions of space where the laws of physics could be slightly different. These walls are anticipated by several notions of symmetry disruption in the early universe. Imagine that space passed through a phase transformation like water turning into ice, but it didn't freeze the same way everywhere. Some regions froze with one set of rules while others adopted a different path. The borders between these patches could become domain walls. Gigantic structures reach over space, distinguishing one cosmic regime from another. In most models, these walls would have swiftly faded or diluted into irrelevance, while some speculative scenarios suppose they could still exist, lurking in deep space like silent sentinels. Going through one could be undramatic, or it might be like walking into a parallel dimension with a slightly another version of chemistry. Your atoms might react just a tiny bit differently. Your tea might taste significantly more citrusy for no apparent reason. Speaking of passing into other realms, some theorists have speculated whether our entire cosmos might be the interior of a bubble. Not metaphorically, but literally. A bubble of space that developed during a time of cosmic inflation. Picture the early universe frothing with quantum fluctuations. In some locations, inflation ceases and a bubble of space forms with its own properties, including the constants of physics, the intensity of gravity, the number of spatial dimensions. Each bubble is a cosmos unto itself. This is frequently dubbed perpetual inflation. And that leads readily to the idea of a multiverse, a foam of bubbles, each with its own distinct physics. In this view, there is a kind of edge where our bubble cosmos meets the inflationary background, or where it might one day clash with another bubble. But such crashes would be beyond rare. If we are a bubble in a large cosmic froth, our neighbors are too far away to ever meet, and the perimeter of our bubble will be more theoretical than actual. Still, there's a peculiar poetry in envisioning the universe as part of a fizzing sea of other realities, each expanding into the empty like soap on a plate. And then there's Gödel's whirling universe. Yes, that Gödel, the same one that poked holes in mathematics with his incompleteness theorems. In 1949, he came up with a solution to Einstein's equations that portrays a cosmos revolving as a whole. Not individual galaxies whirling in place, but the entire fabric of space seem gently bending like a huge cosmic spiral. In this bizarre paradigm, time and space are warped in such a way that you might, in principle, go down a specified path and arrive back at an earlier period in time. Essentially a time loop. Gödel's universe has no edges, but it does blur the difference between boundaries of space and boundaries of cause and effect. What's more disorienting? A wall at the end of the cosmos, or the power to meet yourself before you were born? Now, before you book your round-trip flight to the airport, it's vital to remark that Gödel's rotating world doesn't fit what we perceive. Our universe isn't rotating in that global fashion, and the kind of time loops he foresaw remain speculative at best. But the model is valuable, not because it's physically realistic, but because it expands our brains. It reminds us that the rules of the cosmos are not set by our thoughts, but by calculations, and such equations can allow for worlds stranger than fiction. Another wacky idea argues that the universe might be like a hologram, not in the science fiction sense of flickering projections, but in a very accurate mathematical way. According to the holographic concept, everything that happens in our three-dimensional space might be encoded on a remote two-dimensional barrier. Something resembling the way a hologram stores a whole image in a flat surface. In this situation, the ultimate edge of our universe isn't a wall or a border, but a border where the fundamental information is stored. We're not talking about simulations or digital deception, just a different way of describing the same physics. The notion emerges from string theory and black hole thermodynamics, and it's still hypothetical, but tantalizing. The deeper message behind all these hypotheses isn't that we'll uncover a physical wall at the end of space or a sign that states end of universe authorized personnel only. It's that space could have limits and bounds in ways that don't look like what we're used to. Edges might exist in higher dimensions or in the primordial conditions of our cosmos, or in the knowledge that underlies everything. They might not look like walls. They might look like changes in physics, changes in curvature, changes in the rules themselves. It's certainly plausible that we exist in a universe with no edge at all. But it's also plausible that we're coming up against thoughts that feel like edges, limits of what we can know, of what we can observe, of what our equations can describe. And that's a kind of barrier too, isn't it? We are beings evolved to dwell in rooms on continents surrounded by air and gravity and things that end. So when we step entering cosmology, we bring those impulses with us. We hunt for edges because everything else in life has them. But the universe, like always, is under no duty to obey our expectations. Maybe the cosmos circles silently in on itself. Maybe it reaches infinitely in all directions. Maybe it perches softly on the surface of a higher dimensional bubble. Or maybe, just maybe, it's shaped like something we've never thought of before. Something that twists and joins and folds in ways our minds can barely begin to understand. And yet here we are floating in that unknown, wondering about borders while being part of something that might not have any. There's something soothing in that. Don't you think that the universe may be unending, not just in size, but in possibility? That even the questions themselves might stretch on forever? It's a large enough challenge just trying to fathom this cosmos with its billions of galaxies, whirling black holes, cosmic background radiation, and space that might curve or stretch eternally. We already have plenty to contemplate. But every now and then, cosmologists and physicists like to stir the pot and pose an even bigger question. What if our universe isn't the only one? Welcome to the multiverse hypothesis. It's one of the most fascinating, odd, and fully speculative ideas in current physics. It suggests very simply that there might be more than one universe, perhaps many more, maybe even infinitely many. Universes with different physical rules, different particles, different time frames. Universes where cats walk on ceilings, gravity swings sideways, or your high school haircut selections turned out much better. Before we go too far, let's make something clear. There is no direct proof supporting the existence of other universes. None. We haven't seen them, measured them, waved to them across a dimensional border. The multiverse is a framework, not a conclusion. A way of thinking that develops organically from certain beliefs, but nevertheless lives firmly in the domain of speculation. That's so the idea isn't as outlandish as it might sound. In fact, there are multiple mini variations of the multiverse idea, each with its own taste of cosmic imagination. The first and most intuitive is called the cosmic multiverse or bubble universe model. This idea originates from inflation theory, the fast expansion that occurred immediately after the Big Bang. According to this theory, inflation didn't happen uniformly. Instead, it may have formed several distinct bubbles, each generating its own cosmos, expanding and evolving autonomously. Each bubble might have its own rules of physics. Some could be too odd to sustain matter. Others might have altogether distinct kinds of particles, forces, or even dimensions. We happen to reside in one of the lucky ones where the conditions are exactly right for stars, planets, and long-winding late-night podcasts. In this bubble image, our cosmos is like a single soap bubble floating in a cosmic foam. Other bubbles might exist, constantly wandering, forever separate from ours. If you're imaging a cosmic sink full of dish suds, you're not far off. Then there's the quantum multiverse, which stems from interpretations of quantum mechanics, specifically the many-world interpretation. This version indicates that every time a quantum event has numerous alternative consequences, all of them actually happen in independent branching universes. So in one universe, you hit snooze this morning and stayed in bed. In another, you got up early and made pancakes. In yet another, you tried to prepare pancakes but accidentally found teleportation instead. Each branch is a new version of reality formed by the unfolding of every imaginable option and chance. This isn't merely a mental experiment. It's a serious interpretation of quantum mechanics devised to prevent the awkwardness of wave function collapse. But like the bubble universe hypothesis, it's not anything we can currently test or observe. We can't jump between these branches. There's no interdimensional train station with a mustachioed conductor advertising journeys to the universe where you become a world-famous harmonica player. And indeed, in at least one of those endless branches, you probably have a mustache, even if you've never grown one. Statistically speaking, it's almost guaranteed. Somewhere out there, you might be giving a TED lecture about alternate facial hair choices and their impact on parallel timelines. There's also the mathematical multiverse described by cosmologist Max Tegmark. This is the belief that all mathematically coherent structures exist as physical realities. In other words, if it's mathematically conceivable, it exists someplace. That encompasses not simply alternate universes with different particles, but ones with fundamentally distinct logical rules. Universes where the value of pi is different or time flows in a spiral. It's a strong suggestion, almost supernatural in breadth and probably impossible to test. But it's enticing to consider that arithmetic itself could be the fabric of reality, generating every imaginable version of reality like a limitless library of cosmic blueprints. These multiverse concepts, although intriguing, do meet criticism, and properly so. One of the main difficulties is falsifiability. If other worlds are forever unreachable, how do we study them? How do we know they exist at all? Science works best when we can test predictions, monitor results, and refine our models. When we're talking about realms that can't be reached by any signal, it's hard to apply the conventional scientific instruments. Some physicists see the multiverse as a warning indicator, a symptom of theories extending beyond their functional limitations. Others contend that the multiverse helps explain why our universe has the features it possesses. If there are countless universes, each with various constants and laws, it's not unexpected that we happen to live in one where life is feasible. It's a cosmic form of survivorship bias. We exist here because here is a location where existence is conceivable. It's a bit like rolling dice in a casino with a limitless number of tables. Most tables generate nothing unusual, but at one of them, by pure coincidence, the dice land just right. That's the table we're seated at. We didn't cheat. We didn't rig the game. We just happened to be in the room where the numbers worked out. Some cosmic theories even propose that multiverses might be indirectly detectable, perhaps by unique patterns in the cosmic microwave backdrop generated by collisions between bubble universes. So yet, nothing has come up. But scientists are maintaining an open mind. After all, some of the greatest astounding discoveries in science started off as odd thoughts waiting for the appropriate tools. Whether other universes exist, pondering them widens our imaginations. It challenges us to think beyond the bounds of what we can perceive. It tells us that reality may be considerably larger, stranger, and more humorous than we ever expected. It urges us to be humble in the face of what we don't know and daring in exploring what we might someday learn. And truly, isn't that what science is all about? Not merely answering questions, but discovering bigger ones. Not only growing knowledge, but expanding wonder. Even if we never locate another universe, even if this one is all there is, we've already demonstrated that human curiosity can reach beyond galaxies through time and into ideas as wide as the multiverse itself. That's no minor thing. So whether you believe in a single cosmos or an infinite stack of them, whether you favor one timeline or a branching jungle of quantum possibilities, recall somewhere in the multiverse, you're doing something great or odd or inexplicably involving a llama. And in this universe, you're here thinking about space, sipping tea, and quietly pondering what more might be out there just beyond the curtain of what we know. That in itself is a type of cosmic wonder. Where does space stop? It's the query that brought us here, murmured quietly at the beginning like a toddler wondering if the sky has an end. And after meandering through galaxies, bent dimensions, cosmic microwave whispers, and the margins that may or may not exist, we find ourselves softly looping back to where we began. Still curious. We've learnt that space doesn't behave like a room or a box or a stretch of road. It doesn't come with a fence or a finish line. It doesn't need walls to be complete. It can be unlimited or finite and unbounded. It can stretch, loop, curve, and fold in ways our minds are only beginning to fathom. It can even carry galaxies away from us quicker than light. Not because they're moving, but because the space between us is rising. We know that there is a limit to what we can witness. A cosmic horizon beyond which light has not yet reached us. But we don't know what lies beyond it. Maybe the universe keeps going forever. Or maybe it folds back on itself in a gentle arc we'll never witness. Perhaps our world is one bubble among many, wandering in a higher dimensional sea. Or perhaps the multiverse is merely a poetic thought, wonderful but unachievable. What we do know is that space is not empty. It's alive with structure and subtle vitality. It extends with time. It conveys the light of old stars and the murmur of the Big Bang. It has no core and, as far as we can discern, no end. And still questions persist. Is the world endless or merely incredibly large? Is it curved, flat, or something else entirely? Is it one of many or all there is? And if there were an edge to space, what would be on the other side? We may never find all the answers, but that's not a failure. It's the heartbeat of science. The beauty of the cosmos isn't simply in what we know, it's in what we don't. It's in the quiet courage of looked up and inquiring. Anyway, the hunt continues as it always has through telescopes and calculations, through peaceful dreams and midnight thoughts. Every photon we catch, every map we make, every model we tweak comes us a bit closer. Even if the destination keeps moving like the stars. Maybe that's the whole point. Maybe space never stops. Not because it's limitless in size, but because it's unlimited in mystery. Maybe it doesn't have to finish for it to matter. Maybe it simply is expanding quietly in all directions. An invitation, not a boundary. In the introduction, I asked you a few things. Where you were listening from, what time it was, and whether the question, where does space stop, can keep you awake or soothe you to sleep. I hope by now you feel more relaxed. I hope your ideas have eased into that peaceful area where wonder thrives. And if you're still awake, just barely, I hope you found some serenity in the asking, even if the answer remains distant. Because basically, that's what space gives us. Not merely stars or stillness, but the freedom to ask the biggest questions of all. And perhaps space never stops because questions never do.